All right, so this is my lecture on 13.3, comparing simple harmonic motion with uniform circular motion. There is a relationship between simple harmonic motion and uniform circular motion, and we will apply the related concepts for period, frequency, angular frequency of a spring harmonic oscillator. In other words, a simple harmonic motion, a spring and simple harmonic motion. So uniform circular motion. So I want you to imagine this disc is turning in a circle at a constant speed. And if you can visualize that it has kind of like a ball that's on the edge of this disc, and that is rotating in a circle at a constant angular speed. And I've got a lamp up top that is shining a light on top of that rotating system, and it will put a shadow on this plate, and it will go back and forth and back and forth, and essentially it looks like simple harmonic motion on that plate. Okay, so there is a relationship between simple harmonic motion and uniform circular motion. So that's why we talk about period and frequency with regards to this. So from that relationship, this equation was derived. The period of a spring oscillating on a simple harmonic motion, a spring on an oscillating spring, is defined as 2 pi times the square root of the mass of the block that's hanging on the spring divided by the K constant. And this is what we used in our lab the other day. So we did that lab without really understanding where that equation came from, but now we have a better understanding that it is because there is a relationship between simple harmonic motion and uniform circular motion, okay? And so we know what a period is, which is the time in seconds for one cycle. Mass is in kilograms, and the K constant is newtons over meters. So now that we have this relationship with that, we can take a look and actually derive an equation for the position with respect to time. So even though the spring is oscillating back and forth between some maximum distance, and we have this block and the spring, and we're going back and we're going forth, at any given time, we can actually determine the location of that. So let's kind of figure out what that is. So if I take a look at this position X, so he's moving back and forth, let's just take the position right here at this moment in time. I can say that there is a relationship between X and that amplitude, right? Because amplitude would be the max distance that we are at. So the amplitude is the hypotenuse of that. The X location at that moment in time is adjacent to that angle. And so we know that the cosine of that angle is equal to X, whatever that position is at that moment in time, over the amplitude, which is the maximum distance it would be in this particular simple harmonic motion. So I can rearrange that for X, and I will find X to be equal to the amplitude times cosine of theta. Okay, what is theta? How is theta changing with time? Well, based on its angular speed, we know that angular speed is equal to delta theta over change in time. And so we know that theta, the change in theta with respect to time, is its angular speed times the change in time. So we can replace theta with its angular speed times time, and that will be the amplitude times cosine of the angular speed times its time. And think about that. Angular speed is in radians per second. And if you multiply it times the time at whatever given time interval, and we'll assume that if we assume the initial time is 0, and we just want to know where it is at some elapsed time, Anyway, radians over seconds times seconds is equal to radians, and that makes sense. Now let's go look at our equation sheet, because this equation is actually there. Okay, here it is right there. So notice, however, instead of its angular speed, it has 2 pi times frequency. Where did that come from? Well, let's recall. What do we know about period is equal to 2 pi over omega, which is equal to 1 over its frequency. So let's focus on that part of that conversion factor. Solve for omega. We will find omega to equal 2 pi times the frequency. And if we plug that back into here, we now know where we got the equation for the position x at some given time of a simple harmonic spring system is equal to its amplitude times the cosine of 2 pi, the frequency, times time. Okay, may seem confusing, but I will say this. It is, I have very rarely seen this particular equation used on an actual AP exam, but it does, again, provide you exactly where that block is at a given time if you know its frequency and its amplitude. Okay, you can take the first derivative of this and that will tell you the velocity. You can take the second derivative of this and that will tell you the acceleration for those of you who are in calculus. Just so you know. Okay, position versus time. Take the first derivative, you have velocity versus time. Take the second derivative, you have acceleration versus time. All right, one last thing that I'm going to go over today, and then I'm done. I want you to imagine, once again, this block spring system oscillating up and down. And as it oscillates up and down, it is going to be on kind of like a ticker tape. We have almost like a seismograph, like an earthquake, where it measures the vibrations. But at any rate, there's a little pencil that's sitting on that mass as it oscillates up and down. It's drawing this graph, okay? And we have, oh, here it is. Here is my position versus time equation. X equals a times the cosine of omega times t, which of course omega is equal to 2 pi the frequency. And if I start at its maximum location, I am going to then go through equilibrium, and then I'm going to go to minus a, and then I'm going to go back to equilibrium, and then I'm going to go to my original starting point, okay? And so here's the time it takes to go from where I started back to where I started. And that would be its period. There's one period. There's half its period. There's 3/2 its period, so 1.5, okay? So peak to peak, the time it takes to go from peak to peak is its period. Notice this graph. This is the velocity versus time, and it is the first derivative. So this will be the first derivative for those who are in calculus. And this will be the second derivative. And this is my acceleration versus time curve. And so when I first started and you let go of it, I had a 0 velocity, and then I was accelerating in the negative direction. And then I reached that maximum velocity. And then I had to start heading backwards. So I started slowing down. I changed directions. And so velocity has, you'll notice at this location where I'm right back to where I started from, or actually through my equilibrium position, I'm at max velocity. And notice right here, I'm at max velocity. Where am I at max acceleration? When I'm at my amplitude. Where am I at max acceleration? Where I'm at negative a. Where am I at my max acceleration? I'm at my max amplitude again. And so we actually need to be able to sketch these graphs, and we're going to practice those in class, where I say, okay, we're going to start from, let's say, my amplitude, my height, my farthest away, and I'm going to let go. What does my position versus time curve look like, my velocity versus time curve look like, and my acceleration versus time curve look like. We will be practicing that in class. In fact, actually, we're going to do a worksheet on that. And so that is all I have for today. And we have a homework assignment, and I look forward to seeing you on the next video.